Okay, so these are the contents that you will learn in this chapter. So enthalpy changes, standard enthalpy value, standard enthalpy of formation, combustion, neutralization, and bond dissociation enthalpy, Hesses Law, and the calculate the enthalpy changes using bond enthalpies and enthalpy of formation value, enthalpy of combustion value, and then practical measurement. So the practical measurement, usually we will use what so-called calorimetry. Okay, and I already bring the example of the calorimetry, as you can see here. Can you see? So this one is what we call calorimeter. So it consists of this many things. I'll explain later, yeah. Okay, next one. So first one, we will learn about what is thermodynamics. So thermodynamics, first, a law of thermodynamics. Sorry guys. Okay, first law of thermodynamics. Energy can be neither created or nor destroyed, but it can be converted from one form to another forms. Okay, so we can only change the energy. So energy is actually before and after the reaction, energy is the same. But later on, why we find some different in the calculation and in the experiment. That is because the human error. Okay, and we cannot ignore that. But we still make some error, even though we already make sure that the experiment is carried out perfectly, but still human error is there. Okay, and then next one is energy changes. What is energy changes? So energy changes, you know, in secondary, exothermic and endothermic. When we are talking about exothermic and endothermic, what does it mean? So energy is given out, and energy is and another endothermic is energy is absorbed, given out to somewhere or absorbed to where. So if we are talking about exothermic and endothermic, we have two terms here. You have to understand two terms. So the first one is system. Okay, and the second one is surrounding. Okay, what is system? System is the chemical reaction itself. Yeah, so let's say you mix hydrochloric acid and sodium hydroxide. The system is sodium hydroxide, and the hydrochloric acid. Okay, and the surrounding must be other than hydrochloric acid and sodium hydroxide. It can be the water. What else? When you mix sodium hydroxide and hydrochloric acid, you need a container or beaker. So the beaker is also the surrounding. What else? Thermometer. Thermometer is also the surrounding. So other than your chemical, that must be the surrounding. Okay, so if we are mixing HCl and NaOH, so HCl and NaOH is the system. The surrounding is other than HCl and sodium hydroxide. If you mix hydrochloric acid and sodium hydroxide using steering rod is also the surrounding. Okay, so if the reaction is exothermic, if this reaction is exothermic, it means that the when you mix hydrochloric acid and sodium hydroxide, they will give the heat. Wait, someone is entering. When you mix hydrochloric acid and sodium hydroxide, so the heat will be transferred from the hydrochloric acid and sodium hydroxide to the surrounding. So that is exothermic. When what is endothermic? So endothermic means the surrounding absorb. So your system absorb the energy. So it means that the heat is transferred from the surrounding to your system. Okay. So if heat is given out from the system to the surrounding, that must be exothermic. Yes? Huh? Okay, louder please. Oh, tissue. Okay. Okay, so surrounding, if the heat is given from surrounding to the system, that must be endothermic. So this one is exothermic. Okay. So the example of exothermic is combustion of fuels. And then what else? Here is given respiration. And endothermic is photosynthesis and also thermal decomposition. Okay. So these are the example of exothermic and endothermic. Any question about exothermic and endothermic? No? Okay. Next one, we will learn about the still in the for the still thermodynamics of the enthalpy changes, but now we are going to move to the definition of the enthalpy. So enthalpy is the measure of the heat content of a substance at a constant pressure, constant constant pressure only. Okay, you cannot measure the actual enthalpy of a substance, so we can only measure the change of enthalpy. We cannot measure enthalpy of hydrochloric acid. No, we cannot. But what we can measure is enthalpy of hydrochloric acid mixed with sodium hydroxide, which means enthalpy change of neutralization. Okay, so we can only measure the change in enthalpy. Okay, and enthalpy change, generally it will be written as enthalpy of products minus enthalpy of reactants. Okay, this is the general formula to calculate enthalpy change. But later on, as you learn in JC1, this equation is not always like this. It can be enthalpy change of reactants minus enthalpy change of products. Let's see later. But generally, enthalpy change is you can calculate from enthalpy change of products, the total enthalpy change of products minus the enthalpy change of reactants. Okay, and for exothermic, and in JC1, you have to be able also to draw this one. So reaction pathway of exothermic and endothermic reactions. So please do remember the one at so the axis, the y-axis is the enthalpy or energy. Okay, here is energy. Okay, and at x-axis is the reaction coordinate or reaction pathway. Okay, on the left hand side of the reaction pathway here, that must be reactants. Okay, and on the right hand side must be product. Okay, here is that on the endothermic also, here still reactants, and the right hand side still products. Okay, and the energy needed to make this reaction occur, it's called EA. What is EA? EA is activation energy. Okay, activation energy. Whether it is exothermic or endothermic, they still need activation energy. Activation energy is the minimum energy needed to make the reaction occur. Okay, EA is the minimum energy needed for the reaction to occur. Please do remember that. Whether it is exothermic or endothermic, we still need activation energy. Okay, please take note. And how much the activation energy needed? So usually, if the reaction is reversible, so it means it can go exothermic and also it can go endothermic. If you have exothermic and endothermic reaction, from the energy pathway here, you can deduce that endothermic reaction will need more activation energy compared to exothermic reaction. How do we know? From this purple arrow. So the change from the reactant to the top of the peak, that's what we call activation energy. So if we compare the energy needed from reactants to the top of the peak, this one, compared to that one, as you can see, we need more energy for endothermic reaction compared to the exothermic reaction. And the arrow from the value or the arrow from the reactants energy level diagram to the product, so that's what we call enthalpy change. Okay, and the arrow of the if you notice that the arrow is going down, that means that the value of enthalpy change or enthalpy change, if the reaction is exothermic, the enthalpy change value will be negative. Okay, and for endothermic is the reverse one. So endothermic reaction, as the arrow is going up from reactants to the product, so arrow is going up, so the enthalpy change value is always positive. Okay, and what's next you can notice here is the activation energy. The activation energy, the arrow is always going up. So it means that activation energy is always endothermic because it has it always have positive value. Okay, any question? So if you are asking to draw the reaction pathway of a particular reaction, make sure you write down the reactants on the left hand side and the product on the right hand side, like this, like that, and like that. But the shape will be different for exothermic and endothermic. For exothermic, the reactants must be higher at a higher energy level than product. While for endothermic, the reverse one, the product must have higher energy level than the reactants. Okay. So when you need to draw the arrow for enthalpy change, exothermic will be negative because from reactants to product is going down, and from the if the endothermic, the arrow will be going up, which represents that the value is positive. So positive means needs energy, and exothermic means it's the heat is given up. Okay, from the system. Okay, from system to surrounding. Any question? No? Okay. Next one. So standard enthalpy change. So standard enthalpy change, why do we need to measure the enthalpy change as standard condition? Because enthalpy change is temperature dependent. That's why we have to temperature and pressure dependent. So that's why we have to measure everything in the standard condition. Once we change the condition, the enthalpy value will not be the same. Okay, so that's why enthalpy changes is always represents as this one, like this. So enthalpy change, and then the symbol like this is to represent at the standard condition, and also the temperature here. But usually we just need to no need to write down the temperature, just delta H and then this symbol. That's already that means that the enthalpy change is measured at standard condition. Standard conditions means if the pressure, it must be 1 atmosphere or 101 kilopascal. And if it's the temperature must be 25 degrees Celsius and 298 Kelvin or 298 Kelvin. And also if it's solution, the solution concentration of the solution must be 1 mole per dm cube. Okay. And yeah, so that's all. So the standard condition means this one, the pressure is 1 atmosphere, 25 degrees Celsius, and also if it is solution, the concentration must be 1 mole per km cube. Okay, next one. So we are going to the JC1 enthalpy changes. So the first type of enthalpy is standard enthalpy change of formation. What is standard enthalpy change of formation? So here is the definition of the standard enthalpy change of formation. So the enthalpy change when 1 mole of a compound is formed in its standard state from its element in their standard state. Okay, so what you need to highlight here is 1 mole of a compound is formed. Okay, in its standard state from its element in the standard states. So that is the most important thing you have to memorize. Okay, you have to memorize this one. And the symbol for enthalpy change of formation, standard enthalpy change of formation is delta H. Here, as you can see, delta H with standard symbol, and then following by F subscript. Okay, F delta H, so delta H standard symbol and F. So that is the symbol for standard enthalpy change of formation. So usually you only know delta H and then standard state, right? Standard symbol. But now if there is F on the subscript, so that means that is standard enthalpy change of formation. Okay, and the standard enthalpy change of formation value is sometimes positive, sometimes exothermic, sometimes endothermic, sometimes positive or sometimes negative. It depends on the reaction. It's not always positive or negative. It's not always exothermic or endothermic. It can be exothermic and it also can be endothermic. Okay, and the example of enthalpy change of formation is here. It's given carbon and oxygen, CO2. So 1 mole, please go back to the definition. 1 mole of a compound is formed in its standard state from its element in their standard states. So 1 mole of a compound is formed. What is for the first reaction? 1 mole of carbon dioxide is formed in its standard state. CO2 has gases, right, as standard state, and for form from its element in their standard state. So the element of carbon and oxygen is carbon as graphite and also oxygen as gas. So this one and this one is the element of carbon dioxide. Let's say you have so here is carbon, oxygen. Okay, so enthalpy change of formation of nitrogen dioxide. Nitrogen dioxide. The standard state of nitrogen dioxide is gaseous, right? So if you want to write down the reaction of enthalpy change of formation of nitrogen dioxide, you have to know the element of nitrogen dioxide. What is the element? What elements present in nitrogen dioxide? Of course, we know that is nitrogen. So nitrogen. Nitrogen in standard state, it exists as N2 gas. So it must be N2 gas. Plus oxygen in standard state is gaseous as O2 and write down as gases. And then the last one you have to balance. Can we write down like this? 2 and 2 plus O. I don't write the state symbol, yeah. So 2 and O2 like this. Can we write down like that? Is it balanced? Oh, no, no, no. This must be like this. Can we write down like that? So this one is enthalpy change of formation. And here at the top one, at the top of the, so this one, the reaction 1 and reaction 2. Reaction 1, can we call it as enthalpy change of formation? Enthalpy change, standard enthalpy change of formation. Can we call it the first reaction as enthalpy change, standard enthalpy change of formation of nitrogen dioxide? Can we? Please note if you think that it is yes, it is enthalpy change, standard enthalpy change of formation. Please shake your head if it's not. No. Why? Why it's no? Why your answer is no? Okay, please, Kevin. What do you think? Yes, because the compounds produced is 2 moles. Well, the definition of enthalpy change of formation, standard enthalpy change of formation, is 1 mole of a compound formed in its standard state from its element in their standard states. Yes, the element is still in the standard states. If I write down the state symbol, yeah, but state symbol is the same for reaction 1 and reaction 2. But we cannot call this reaction as having enthalpy change of formation. No, we cannot. Why? Because there is 2 moles here. So it's not following this one, right? So that's why the enthalpy change of formation is the reaction number 2. So what we call, so what is the name of the enthalpy change in the reaction 1? So what's the name? So in general, if there is, if it's not following the definition of enthalpy change of anything that you study, we just need to write down as enthalpy change of reaction. So the symbol is delta H R, standard symbol, and then R. Okay. So if we cannot classify the enthalpy change of a reaction, we just need to write down enthalpy change of reaction. Okay. But if this one, for example, formation of nitrogen dioxide, so we have to write down enthalpy change of standard enthalpy change of formation of nitrogen dioxide. Okay. Delta HF standard and then NO2. Like this. For the first one, so NO2, still NO2. Okay, but 2 moles for the first one. Okay, any question? Okay, I hope no more question. I hope no question, yeah. So you just need to go back to the definition. And then how do we know the elements of each element? So you have to memorize, no other way. So usually elements in group 17, they will exist as diatomic molecules. For example, F2, Cl2, I2, Br2, something like that. Nitrogen is exists as N2. What about sulfur? Sulfur can be S or it can be S8. Okay, sulfur is exists as sulfur single atom, or you can also write down as S8. Okay, S8 is the element of sulfur. What about phosphor? Phosphor is P4. Okay, elements of what in the periodic table? Element of sodium, sodium metal. So Na metal, solid, yeah. Solid, this one is solid, this one is solid, this one is solid. Standard state. And what else? Iron, iron solid. What about mercury? Mercury is liquid. Okay, even though mercury is metal, but it is liquid in its standard state. Any question? No? Okay, I'll erase, yeah. Don't worry, I record this lesson so that if you miss something, you can go back to the recordings later. Okay, next one is standard enthalpy change of combustion. Okay, standard enthalpy change definition of combustion definition is we must read the definition. 1 mole of a substance undergoes complete combustion under standard conditions. All reactants and products are in their standard states. Okay, so 1 mole of a substance undergoes complete combustion under standard conditions. And everything in the reactants and products must be in their standard states. Okay. We meet again with this reaction, carbon and oxygen. It's similar, right? Like in the previous slides. Enthalpy change of formation. We have carbon and oxygen becomes CO2. And then in combustion, we meet again, carbon and oxygen becomes carbon dioxide. Yes, it is correct that carbon plus oxygen becomes carbon dioxide. We can write down, we can define this enthalpy change as enthalpy change of formation as well as enthalpy change of combustion, because this reaction define those two enthalpy standard enthalpy change, those two types and standard enthalpy change. Why? As you can see, the previous one we have I already explained, yeah, why carbon plus oxygen becomes CO2 is enthalpy change of formation. Now let's analyze this one. Why this one is enthalpy change of combustion? So go back to the definition. 1 mole of a substance undergoes complete combustion. 1 mole of a substance undergoes complete combustion. Combustion means plus oxygen, and the product must be carbon dioxide and or water. Okay. Since here there is no hydrogen, so the product must be only carbon dioxide. Okay, so this one is the enthalpy change of combustion. The symbol of enthalpy change of combustion is delta Hc. Delta Hc and then standard state. A standard symbol, the circle one with something like theta. Okay, so that is enthalpy change of combustion. What about if you have methanol? Yeah, ethanol here. So this one is ethanol, yeah. Ethanol. 1 mole of ethanol, 1 mole of a substance undergoes complete combustion under standard conditions, and all reactants and products are in their standard state. So here, in the third reaction here, everything is in their standard state, right? And also, the reaction is complete combustion. Complete combustion means it produces carbon dioxide and water only. There is no carbon monoxide and there is no unburned ethanol. So that must be complete combustion. Okay, complete combustion is indicated by the product of the reaction is carbon dioxide and water only. Okay, so this one is also enthalpy change of combustion of C2H5OH. For this one, enthalpy change of combustion of carbon. Okay. Have you noticed that when the previous one, oh, okay, maybe we focus on this one, yeah. Oh, undo. Okay. So if you notice, for the first reaction, we can also write down enthalpy change of formation of CO2. Okay, so if you write down enthalpy change of formation, you have to write down the product, because 1 mole of a substance is formed back to according to the definition of enthalpy change of formation. But if you want to write down enthalpy change of combustion of a substance, you have to write down the reactants. What is burned? So here you burn graphite, right? Carbon. So it must be enthalpy change delta Hc of carbon. Delta HC, carbon. But if you want to write down this reaction as enthalpy change of formation, you have to write down the substance that is formed. So here the substance, 1 mole of substance that is formed is carbon dioxide. So write down as delta HF and then standard state and then CO2. Okay, any question? Is it clear? Okay. Next one, the last one in this in JC1 is enthalpy change of neutralization. Look at the definition. The enthalpy change when 1 mole of water is formed from its ions in dilute solutions. Okay, 1 mole of water is formed from its ions in dilute solutions. Okay. Oh, before I forgot, so let's go back to the previous one. Enthalpy change of combustion is always exothermic, meaning that the value is always positive. When you calculate enthalpy change, later on, when you calculate enthalpy change of combustion and you get positive value, you have to recalculate. Because enthalpy change of combustion is always negative, it's always exothermic. Why? It's impossible when you burn something, then you don't feel any heat. It's not, so it means that your reaction is not occurring. Okay, enthalpy change of reaction is always exothermic. And as well as neutralization, the enthalpy change value is always negative. It's always exothermic. Later, if you calculate enthalpy change of combustion of neutralization and you get positive value, recalculate. Your answer must be wrong. Okay. And 1 mole. Okay, go back to the definition. 1 mole of water is formed from its ions in dilute solution. So it depends on the reaction. If your reaction producing only 1 mole, so that must be enthalpy change of neutralization. Let's take an example. So let's say you have HCl plus NaOH. So the product must be NaCl plus H2O, right? So this one is enthalpy change of neutralization. Okay. It will be different if you have H2SO4 plus NaOH, that must be Na2SO4 plus 2H2O. Okay, something like this. So the enthalpy change of neutralization here, because it's reducing 2 moles of water, so whatever value given here, you have to divide it by 2, because according to the definition, it's 1 mole of water formed. So please be careful when you find this kind of reaction. So let's say the delta H value is 100. Okay. So what is the delta H of neutralization of this reaction? So you have to divide it by 2. 100 divided by 2. So it is 50 kilojoule per mole. Okay. Be careful with the chemical equation. If the chemical equation producing only 1 mole of water, so you can just use the enthalpy change value. But if it's producing more than 1 mole, so you have to use stoichiometry, something like stoichiometry. So if it's producing 2 moles, so it means you have to divide it. So it means you have to divide the enthalpy change of value there divided by the coefficient of the water produced. Okay, any question? No? Okay, next one. Please answer this question. Magnesium carbonate becomes magnesium oxide and then CO2. What type of enthalpy change is that? Okay. Why I cannot see enthalpy change of blah blah blah. Okay, time's up. So what is okay, yeah? So most of you answering, okay, most of you answering the first one, yeah? So let's see. Enthalpy change of reaction. Yes. And what about the rest? Some are answering the second one and the third one. Okay, let's see. Enthalpy change of reaction, enthalpy change of formation, enthalpy change of combustion. Okay, so magnesium carbonate, standard state is solid, right? Magnesium oxide is solid. Carbon dioxide is gaseous. Okay, according to the definition of enthalpy change of combustion, is it combustion? No, it's not combustion. No oxygen. If it's combustion, substance plus oxygen, it will produce carbon dioxide and water. It's producing carbon dioxide, but there is no oxygen. So it means oxygen in the reactant, right? So it's not, it means that it is not combustion. It is not combustion. It is also not formation. So it must be enthalpy change of reaction. Okay. Do you understand? Any question? Or miss, it must be combustion because it's producing carbon dioxide. Yes, it's producing carbon dioxide. But if it's combustion, it must be magnesium carbonate plus oxygen. Oxygen means you burn something. Okay. Okay. Do you have question? Is it clear why this is enthalpy change of reaction? When you cannot classify, then enthalpy change of combustion. Enthalpy change of reaction. Okay, next slide. Please answer the second type of enthalpy change. You have only 30 seconds. Okay, what type of enthalpy change is that? We just discussed, yeah. So if you get confused, can you select more than two, more than one? Sorry, cannot. Okay, that's okay. Okay, yes. Okay, so some are answering enthalpy change of formation, some are answering enthalpy change of combustion. Both, if you're answering formation and combustion, you are correct. Okay, because this kind of reaction is this one this reaction can be classified as enthalpy change of formation as well as enthalpy change of combustion, because it's combustion producing carbon dioxide and there is oxygen here and 1 mole of substance that is burned, and also it is formation because 1 mole of carbon dioxide is produced from its element in their standard states. Okay, any question? No? Okay, next one, please answer the third one. What type of enthalpy change is it? Okay, 7 seconds. 4 seconds remaining. You may change your answer. Oh, but time's up. Okay, let's go back. Some of you answering the second and the fourth. Okay, enthalpy change of formation, and some are answering enthalpy change of neutralization. Okay, let's have a look on the question. Hydrochloric acid in the gaseous state, and then NH3 ammonia at the gaseous state, and also NH4Cl in the solid state. Oh, okay. So it's okay. rejoin again. Can you? I mean this one is the code, Tania. You can rejoin again. Oh, sorry. Okay. So some are answering enthalpy change of formation and enthalpy change of neutralization. So if we look at the reaction, hydrochloric acid and ammonia, is it the element of hydrochloric acid? So it's the forming ammonium chloride. This reaction is about the forming of ammonium chloride, right? If we have to look at the enthalpy change of formation, meaning that the forming of one mole of substance from its element. Hydrochloric acid is not element. Ammonia is also not element. So we cannot classify this one as enthalpy change of formation. Element of hydrogen is H2 gas. Chlorine is Cl2 gas, right? Nitrogen is N2 gas. So we cannot classify this one as enthalpy change of formation because it's not from the elements, from its elements, right? Next one, if you classify it as enthalpy change of neutralization, it seems like it is acid and base reactions. But is there any water produced there? No, so we cannot also classify this one as enthalpy change of neutralization. Okay, enthalpy change of combustion, of course, it's no. So it is enthalpy change of reaction. Okay, do you get it? Okay, good. Students at home, do you have question? No, okay. Next one, the last one, I think. I forgot how many questions I put here. Okay, this one, easy. Please vote. 23 seconds left. You may also change your answer. You still have time. Okay. 3, 2, 1. Time's up. Okay. Wait. Okay. So what type? Oh, so most of you are answering enthalpy change of the second one. Enthalpy change of formation. Enthalpy change of formation. Yes, it's correct. It's enthalpy change of formation. 1 mole of water is produced from its element. What about if you are answering enthalpy change of neutralization of what's next? Neutralization. No, we cannot say this one is enthalpy change of neutralization. Yes, it's the forming of water, 1 mole of water, but it's not from its ions. The water here is forming from its element. So it's incorrect if you are answering enthalpy change of neutralization. Okay, so you can answer this one as enthalpy change of formation. Yes, it's correct, but you cannot answer this one. What about enthalpy change of combustion? Why? Why cannot, Romano? Okay. One. There's no carbon dioxide. Is it? So this one is, we can define this one as enthalpy change of combustion. Okay, the truth is we can define this as enthalpy change of combustion because you have 1 mole of a substance that is burned, complete combustion. Complete combustion, as I mentioned before, it can produce carbon dioxide and or water. As long as you put oxygen on the reactants, that is enthalpy change of combustion. The product of the product of combustion, complete combustion, must be carbon dioxide and water. Doesn't mean that carbon dioxide and water must be present both. No, one of them can be it can be one of them. it is impossible to carbon dioxide as the products because there is no carbon. So it's okay. There is if there is no carbon dioxide. Okay, so it's still enthalpy change of combustion. And if you are answering this one, is also correct, but it's since you are in JC1, so I expect that you will never answer this one when you find this. Okay, so this one enthalpy change of reaction is also correct, but this one is just general terms of enthalpy change when you cannot classify. So this, if you can classify, specify what type of enthalpy change is it is, so please classify. But once you cannot classify, then it's okay to answer enthalpy change of reaction. Okay. Next one. Is it the last? Oh, no. One more. This one? What type of enthalpy is it? What type of standard enthalpy change is it? Only 13 students answering, yeah? So where is the rest? Okay, time's up. So let's go to the full question review. So reaction and enthalpy change of neutralization. Okay. Oh, like, okay. Okay. Yeah, at least you have your own answer, right? And then you will know which one is the correct one. Okay. Whether your answer is correct or not. So please assess yourself if you got disconnected. Okay, so HCl and NaOH becomes an ACl and H2O. 1 mole of water is produced from its ions. Ions mean from its solution, from solutions. So the correct one must be enthalpy change of neutralization. Okay, enthalpy change of neutralization. If you answering enthalpy change of reaction is also correct, but it's not in JC1 level. Okay. I hope you are answering. If you find this kind of equation, this kind of chemical equation, producing 1 mole of water from its ions, it must be enthalpy change of neutralization. Okay? Oh, why so many questions? This one? Must be easy, yeah? Be careful with sulfur dioxide and water that they are not elements. Okay, element of sulfur, as I said before, S or S8, and hydrogen is H2, oxygen is O2. So it must, so your answer is enthalpy change of formation. Okay, so please be careful. The element of sulfur is only S as solid, or sulfur 8 S8 as solid. Oxygen is O2. Hydrogen is H2. So it must be enthalpy change of reaction. Okay, so it's not enthalpy change of formation. We cannot say that. Okay, next one. I think this one is the last one. Okay, next one is the bond dissociation enthalpy. Usually you will we just call it as bond enthalpy. We skip the dissociation enthalpy to be short for to shorten the term. So we call it as bond enthalpy. So the definition of bond enthalpy is energy required to break 1 mole of gaseous bonds to form gaseous atoms. Okay, so there are many methods to calculate the enthalpy change. So the previous one, when the total of enthalpy change of products minus the total enthalpy change of reactants, that is the first method. This is the second method. So you can break down the bonds of compounds, and later on you can calculate the enthalpy change of reaction. Okay, so the value of bond enthalpy is always endothermic. Why? Because as according to the definition, energy required means you need energy from outside. Energy from outside means it is endothermic. Okay, energy must be given. Apa? Enggak tahu. Enggak kayaknya. Enggak kok. Insya Allah cukup. Thank you. Okay, so the strength of so bond enthalpy, yeah. So it's specific for every bond. So when you have carbon and carbon, if it's single bond, double bond, triple bond, so the strength of every bond to be we need to break down, we need to overcome is different. The more bonding, when you learn chemical bonding, the more bonding, the more energy we need to put so that we can break down that bonding. Okay, it is so the value of the bond enthalpy will be given in the question paper unless you are asking to calculate the bond enthalpy. Okay, so it is given here. So hydrogen and hydrogen is 436, and the value and the unit is kilojoule per mole. Okay, and it's all here. And if you have, for example, chlorine becomes chlorine atom, chlorine molecule becomes chlorine atom. So how much energy do you need to break down Cl2 in a gaseous state becomes Cl atom in a gaseous state? So you can look at here. So the value, the energy you need to give to the chlorine is about 338 kilojoule per mole. Okay, and if it's water, how much energy you need to break down water molecule? So water, chemical bonding HOH. So the bonds of water is HOH. So it means you need 2 OH, right? 2 OH. So calculate. So here OH is 463. So meaning that you need 2 times OH is 463. So that is the energy you need to break down OH bonds. Okay. Okay, so this one is Hesses Law. So Hesses Law, we will learn more later, yeah. So it's just short review about Hesses Law. So Hesses Law says the enthalpy change is independent of the path taken. Okay, what does it mean? So if you see here, we have A and B. From if we want to change A becomes B, we need this amount of energy, delta HR. Okay, this means that to change A to become B, we need this much of enthalpy change of reaction. Okay, we cannot write down what is the enthalpy change of reaction because it's not reaction, it's just analogy. If you want to change A becomes B, you need delta H of reaction. Okay, but let's say this reaction is not easy. You cannot conduct it in the lab. So you can calculate the delta HR using indirectly from that way. And the value will be the same. Okay, so delta HR is this one, right? The value, let's say the value is 1000. But you cannot calculate this one in the experimentally in the lab. So you can use indirect way using that way. From there to there and then there. Okay, so you can form another substance to calculate that enthalpy change of reaction. And the total enthalpy change taken here will be the same as delta HR. Okay. It's similar like you are calculating resultant factor, right? So it's similar. The arrow also important to the value. Okay. Usually, I will suggest my students to use clockwise and anti-clockwise. So imagine this is a clock, and this one is clockwise, and this one is anti-clockwise, right? So clockwise equals to anti-clockwise. So clockwise, in the clockwise, there is delta HR. Delta HR equals to anti-clockwise. Anti-clockwise means delta H3 plus delta H2 plus delta H1. Okay, so this is the, okay, Flora. So this is one of example of the reaction, yeah. So we can, let's say we want to know the delta HR. So yeah, so that is the total of delta H1, 2, and 3. But if in the question we know this value, we know this value, and we know this value, and you have to calculate delta H2. So you can also still use Hesses Law to calculate delta H2. Then you need to rearrange this equation using your mathematical knowledge, rearrange that and calculate delta H2. It seems easy, but later I know that it will not be easy. Yeah, let's study this together. Okay, so this one is the idea of Hesses Law. Okay. Next one. Okay, Hesses Law, we can calculate so many things of enthalpy change here. That's why I said in the beginning, enthalpy change can be calculated from the total of enthalpy change of product minus the total enthalpy change of reactant. Is not always like that because there is Hesses Law and many types of enthalpy changes. So later on, you have to understand this one as well. Okay, so the first one, the first application of Hesses Law is this one. Enthalpy change of reaction from bond enthalpies. So when you break down the bond, it means that you need energy from outside, right? And when you, so usually when you are in Sec 3, delta H of reaction is equals to bond breaking minus bond making, right? Bond breaking means this one is from the reactants and this one is from products. Actually, this formula is derived from Hesses Law. So let's say you have reactants and becomes product, becomes delta HR, right? And then it's changed to gaseous atoms. Gaseous atoms means you need information from bond enthalpy. And also, products is also there. So if you are using Hesses Law, then you will know that bond breaking minus bond making. So if we have used this one, delta HR clockwise is equal to anti-clockwise. Clockwise delta HR equals to bond enthalpy from products to gases here, yeah, products to gaseous atom, meaning that it must be forming. So forming means negative delta H of product, yeah, plus bond enthalpy change of the reactants, so delta H reactants. So here is product. So that's why the bond enthalpy is delta H of reactant minus delta H of product. Sorry, it's not delta H, yeah, bond energy. Bond energy. This one also bond energy. Okay. So that's why delta HR is bond energy of the product, reactants minus bond energy of the product. Okay. And if the bond energy, the total bond energy of the product is bigger than the total of bond energy of reactants, that must be exothermic. Why? Because the negative value is bigger than the positive value. If the enthalpy change of the reactant is bigger than enthalpy change of product, the bond energy of the product, that must be endothermic. Why? Because the positive value is bigger than negative value. Okay. Okay, bond breaking minus bond making. That one. So this one is it's bond enthalpies of reactants minus bond enthalpy of products. So that's what you learn in secondary 3. Okay. So the formula is derived from Hesses Law. Okay, next one. Yeah. So this one, when you have a compound, you have to draw the compound every bonding, every bonds in the compound. So for example, here you have 18. You have 18. So CC double bond here, you have to draw it so that you can select which bond energy you need to use. Okay. If you are using CC and then single bond, it will be incorrect because the value is different. Okay, so that's the important thing why you need to know the chemical formula or the display formula of a substance. Display formula means you have to draw every bond in a compound. Okay, so from this information, then you can calculate this one becomes this one. So the total bond enthalpy here minus the total bond enthalpy here. Okay, and what does it mean here? CC hydrogen without bonding. So this one is the atom. Yeah, remember the previous one, gaseous atom. So this one, according to Hesses law, reactants it will become gaseous atoms and then products. So this one in the one and on the right hand side here, the one on the top, the one on the bottom here is the gaseous atom of every atom here. Okay, so we can calculate this one using this minus this. Okay, so you can use bond breaking minus bond making. Bond breaking means total bond enthalpy in the reactants minus total bond enthalpy in the product. Okay, so this one we will continue tomorrow. We will continue tomorrow. So tomorrow I will use your PE. Sorry guys, because we are very late right now. So tomorrow will be no PE. There will be chemistry. Okay. And for now, please join the start. Okay. Please join the start live quiz here. Sorry, email. Okay. So here I have quizzes. So please join. Okay, class. There will be no homework for today. We will continue the enthalpy changes tomorrow with Hesses Law. Please be prepared to review today's lesson so that tomorrow you can follow the lesson. Because tomorrow Hesses Law is quite complicated. I would say it's quite confusing. But if you follow the my suggestion, I think it will be easier. Okay. Tonight, please review today's lesson so that tomorrow we will go smoothly. Okay, how many more? 19. So 2 more. Maria Flo already here? Not yet. Okay, so it must be 22 students, yeah? 2 more to go. Please, if you haven't joined, please join. 1 more. And then we will start. Okay, well, waiting for 1 more students. I think, yeah, 1 more student. I think we can start. Okay, complete. Go.